Then another term we use is Fresnel Zones. So if this is the transmitter, base station, BS, if base station is the transmitter and MS, mobile station, receiver, if you were to plot an ellipse with those two as the focal point, you know how to draw an ellipse? Some of you must have drawn in high school using a string. You can put two pins and take a string and then put your pencil around and you can get an ellipse, right? So that's what you have to do. So if you draw that ellipse, all points on the ellipsoid have the same BS, MS run length. Run length means this plus that is fixed, constant, right? Because you took the string and then you moved around. So this line, this angle line and that angle line, they add up to the same value on every point. And so these are called Fresnel ellipsoid for which the run length is line of sight plus I lambda by 2. I is equal to, you put 0, you get line of sight. I equal to 1, you get line of sight plus lambda by 2. So if you put a string such that this thing is length of line of sight which is already there plus this is lambda by 2, you get the first ellipsoid. Then you can draw another one with 2 lambda by 2, 3 lambda by 2, third one, 4th lambda by 2, 5th lambda by 2. So you'll get lots of ellipsoid like that. All Fresnel ellipsoid result in a phase shift of I upon pi. Alright, it should be really the signal pi, not pi, symbol pi. So I upon pi, and this should be I divided by, not backslash. Radius of the ith ellipsoid, at distance dt from the transmitter and dr from the receiver is I times lambda, this is I, times lambda times dt upon dt plus dr. So anyway, so the free space d square law is followed up to the distance at which the first Fresnel ellipsoid touches the ground. Now if these were high in the sky, then this is a ground here, and this is the first Fresnel zone. Wherever it touches the ground, up, that is the distance up to which the d square law is followed, and after that it doesn't, right? We also saw that d break. So that's how we got this formula for d break, using these things. Basically you have the antennas and there are Fresnel zones around it, and basically depending upon where you are in which Fresnel zone, the signal properties are different. So we know a lot about how the signal propagates, and we are going to talk about now few other things, details, physical layer, and we will be done with the physical layer I think in this module, and then we will be talking more about the higher layers. But few other things that the electrical wireless communication people talk about are the diversity or multi-antenna systems. So previously we used to have one antenna, but now most of the things have more than one antenna. If you buy a router today, this will come with 3 or 4 or 5 antennas, right? And so we'll talk about why those things are used. And so receiver diversity, transmitter diversity, beam forming, and MIMO. I'm going to talk about one by one. Receiver diversity means that the receiver can have many antennas, and then when it receives the same signal from this antenna, this antenna, this antenna, that antenna, it could multiply by A1, A2, A3, AM and then add them up. And so now, depending upon what value you choose for A1 through AM, you will get some received signal. So this is called receiver diversity, because the receiver is putting many antennas and then trying to get signals as much as it can. Now how it can combine? It can do selection combining. That it could just measure the signal to noise ratio on each of these antennas and then just take the one which has the highest signal to noise ratio, which means the lowest noise, highest signal. Right? So we will just select one antenna and then we don't worry about the other antennas. And then the next minute we again measure it, and next second and next microsecond. We again measure it, and then we take the antenna with the best SNR, We could do threshold combining, in which case select the first antenna with SNR above a threshold. So if this one has high noise, we go to the next one. If it has good enough noise, we just stop right there. Maximal ratio combining. So the phase is adjusted so that all signals have the same phase. So we could put some value for A1, A2, A3. By the way, A1, A2, A3 do not have to be real numbers. They could be imaginary numbers or complex numbers. Okay. So generally in these fields, we talk about complex numbers because A plus Ij, because you see the horizontal and the vertical component, and then, so if you want to put 45-degree phase, you will have same A and B, A plus Ib. That will become 45-degree. Right? So the imaginary part is vertical, the real part is horizontal, and so the whole thing is a complex number. Yeah.
Why should we use threshold combining?
Why should we use threshold combining? I want to produce a very simple algorithm. I don't want to do too much. So there is no reason. Basically, it's the designer's decision that this is good enough and I don't want to do any complex multiplication, division, and this and that. Okay?
Selecting the horizontal makes more sense,
I know. I'm not going to argue about one against the other. People have suggested, and these are possibilities. And it's not necessary that you say one or the other. When you really design it, you will know much more than this. Right? So some way, all I'm saying is I'm just giving you diverse opinion about diversity so that you know that it is basically many possibilities of how you combine these things. Same thing the transmitter could do. Transmitter could have many antennas, and then it could put different signals on each of them. It could multiply by some complex numbers and then transmit. And so ample space, power, and processing capacity of the transmitter. And this might be done particularly if the transmitter has a lot of money, which generally is the case. So cell phone company has a lot more money than we do. So cell phone company might put 10 antennas, and while we have little money, so we can only buy with one antenna or two antenna a cell phone. So in that case, the transmitter will have diversity and we all benefit. And if the channel is known, we can find out the phase of each component and weigh in before the transmission. So this is what we haven't done is basically the channel is estimated continuously. So we continuously see what is sent, what is received, and we figure out what is the channel model, and depending upon that we can adjust these values. If the channel is not known, then we use something called, another magic which is called space-time block codes, and I'm going to explain that too. If the channel is not known, then we use space-time block codes, which we'll talk about later. But before that, beam forming. Beam forming is basically making the antenna directional. So the antenna is directional, and that is like, you're putting your ear, if you want to receiver directional, then you put your ears towards the source somehow, and if you want to have transmitter directional, then you put your transmission that way. And so the interesting thing is that you can change the direction continuously. So I could transmit to this direction and then change in a microsecond to that direction, to that house, and then transmit and come back to this. So there are antennas which can change the direction continuously. Now, of course, they can move. If you are going to go to this satellite, that satellite, then they will come at the beginning of the year and move your antenna for the rest of the year. It is pointing to another satellite, but that is not what we are talking about here. Here we are talking about something which doesn't move, but the signal changes. So by phase shifting various received signals and then summing, we can focus on a very narrow directional beam. Our digital signal processing is used for signal processing and self-aligning. So digital signal processing, I use the word DSP. So that's a whole field of DSP, digital signal processing, where you take different matrices and then you multiply them and you somehow get the result. We are not going to go there, but you have to just know that there are such things. So they can do beam forming, and beam forming, all it means is making the signal directional towards the receiver.